talked to, great scientifically. And I think he's been well, I would say it's a mainstay in our group, especially with respect to graphene synthesis, device fabrication. He's been the go-to guy. And I think we all owe him many debts of gratitude. Thank you again. And with respect to the work, well, I'll let the work and Nirjhar speak for themselves. Go for it.
All right, thank you everyone for joining here with me for my PhD defense talk. My name is Nirjhar Sarkar, and today I'll be talking about strain engineering of two-dimensional materials by scanning tunneling microscopy. And before we start the talk, I want to show you a 1-minute video clip that was developed by IBM.
Brought to you by.
So these were carbon monoxide molecules on a copper surface. And this video was developed 10 years ago, but the idea was actually started by a physicist from UCSD. His name is Don Eigler, and he actually went to IBM and moved xenon.
He was a student here
at Mayer Hall,
UCSD,
and his PhD thesis was on STM. And he went to IBM and he moved xenon atoms on a nickel surface, and he wrote IBM with it. And that's how it all started from there. Then after that, Don Eigler and Mike Cromie took 48 iron atoms and they arranged them in a circle. And they wanted to exhibit the electronic wave function. But there is something common with all of these materials. And that is that these are called as add atoms, meaning they're adsorbed on the surface. They're weakly bonded on the surface. So now when you have arranged add atoms on the surface, when you would want to image them, you would want to make sure that the tip height is greater than the bond length. Otherwise, you would move those add atoms. Now, that is called as the imaging mode. So now, what is the manipulation mode? In manipulation mode, now you would want the tip to be closer to the add atom. When you do that, the interatomic interaction between the tip and the add atom now is stronger enough to drag these add atoms on the surface. So it's interesting to observe that how a simple idea like this of bringing a tip closer to an add atom gave us so many pretty experiments. And now I want to showcase to you a simple idea where let's remove this add atom and let's bring the tip closer to the surface. Now in this scenario, there is interatomic interaction again between the tip and the surface, but will this interatomic interaction be strong enough to deform these kind of surfaces? And the only way to know would be to, that would kind of depend on the type of the surface. Like for example, if I bring the tip closer to a rigid bulk metal, then there would be no warping. But now let's consider the scenario that we have taken a two-dimensional material where which has a software surfaces which are made up of single atomic sheets of carbon stacked upon one another, carbon or other elements stacked upon one another with weak van der Waals forces. And so there is a high possibility that these surfaces might get deformed. And so for this series of experiments, I have chosen graphite as my material because graphite is single atomic layer, weakly bonded on top of each other, in contrast to niobium diselenite and molybdenum disulfide and other 2D materials that are triatomic. So this brings us to the outline of today's presentation, where we are going to bring a tip closer to the graphite surfaces, and we are going to find as many features as we can, like step heights, grain boundary, moire patterns, and we are going to deform all of them, and we'll see how far we can go with this simple idea. So let's start with a step height. This is a simple three-dimensional schematic of a step height, and this the step terrace is over along the red line that you see over here, and this step height is of a size of an atom, so it's a monoatomic step height. So now I've taken a three-dimensional image of a monoatomic step height on a graphite surface with the STM, and the light green layer is elevated up, the dark green layer is elevated down, and so the step height is along that red line. So now let's draw a topographic line along this red line. And so I also want to point out that each of these little dots that you see, they're individual carbon atoms. So now let's draw a topographic along this red line. And we see that the topography, this is elevated up, this is the grain elevated up, this is the grain elevated down. And we see that there are hills and valleys over this topography. So every hill over here corresponds to a single carbon atom. So now we can position all these carbon atoms underneath. And the step height is going to be the difference between these two domains. I also want to point out that everything here we are drawing up to scale, 1 angstrom on the right axis, 1 angstrom on the left axis. So now let's bring the tip closer to the surface, and we can do that by increasing the tunneling current. So on increasing the tunneling current from 3 to, let's say, 30 nanoamps, the tip comes closer to the surface, and let's observe how the topography is going to change. And we observed that the topography is actually changing. And this was the anomaly that was noticed first in 1986, that how is it possible that a height of an atom goes up by several angstroms, several orders of magnitude, just by changing tunneling parameter conditions. And there are many models that came off from this observation. Some were electronic-based models, some were dirt-based models, but none of these models kind of satisfy the series of experiments that I have done here. And so the idea is to understand this anomaly. And so we have come up with a model that the only way to explain that kind of fits our observation, our experiments, was that if we consider the possibility that each of these atoms are being pulled off the plane. So we'll see later on by the end of the talk how this model is accurate, and it explains most of our observations that we have seen so far. And so let's first start with measuring the atomic amplitudes, estimating all the atomic amplitudes as a function of current. We have two data points, 3 nanoamps and 30 nanoamps, but let's fill this up more and also measure the constants, the step height as a function of tunneling current. So that brings us to atomic deformations on the y-axis and as a function of tunneling current on the x-axis, where the gap is reducing as we increase the tunneling current. So the deformation is on the rightwards direction. And so the atomic amplitudes we see is going up and up, but the graphite step remains constant. And that is kind of interesting because now the graphite step, the fact that it remains constant, irrelevant of these tunneling currents or the gap distances, tells us, reaffirms our belief that a step height is a reliable calibrated feature in the z direction. Now, this was all done on graphite, and I kind of wanted to test this deformation idea and on other materials as well. So I chose niobium diselenite for our experiment. So what I did, I found a series of monoatomic steps on niobium diselenite, and these are a series of monoatomic steps or unit cell steps. A single unit cell is made up of selenium, niobium, selenium. And when we do repeat the same experiment of measuring the atomic heights and the step height as a function of current, we observe this. We observe that the step remains constant just like the graphite step remains constant. Both of these numbers, 12.5 and 3, are the lattice constant of graphite and niobium diselenite. But what is interesting to observe is the deformation of the atomic heights of niobium diselenite is smaller than that of graphite. And why is that so? We are applying this, you're using the same tip, we are applying the same amount of deformation, but niobium diselenite gets deformed by a lesser amount. And the answer might lie in the crystal structure. So if we compare the crystal structure of graphite and niobium diselenite, graphite is made up of single atomic carbon sheets stacked upon one another, whereas niobium diselenite is made up of selenium, niobium, selenium sandwich, a triatomic sandwich. Now they're all bonded by weak van der Waals forces. Now, if we bring down the tip closer to the surface, we see that there's a possibility that graphite gets deformed by a larger amount because graphite is thinner. Every unit cell is thinner, saying it's single atomic, whereas niobium diselenite, a unit cell is thicker, so it's triatomic. Another thing to point out is whenever you're trying to deform any material, that will try to resist that deformation, and that resistance would be in the form of shear, and the shear would act along the van der Waals forces, along the van der Waals directions, and this shear would depend upon the bulkiness of each of these layers, where niobium diselenite is heavier, so there would be a higher shear force. Whereas in the case of graphite, since it's lighter, there will be lesser shear force. So there will be a less restoring force involved in the case of the graphite. And so that's why we observe that graphite gets deformed by a larger amount than niobium diselenite. And so this kind of brings us to the end of the step story. And I want to point out here that it's interesting to see that a step edge, which is a one-dimensional defect, a step edge is telling us a lot about the material. And there is more information that you can get from a step edge. Like, for example, this is a three-dimensional image of the monoatomic step height. Let's look at how the two-dimensional image looks like. And looking from a distance, this two-dimensional step edge looks very rough, and it doesn't look like it has a fixed direction. But if we look carefully, if we zoom in into this white dotted box, if we zoom in, we'll find out that we can look at individual atoms, and all of these tiny, tiny dots are individual carbon atoms. So you can find out the symmetry of these carbon atoms, and these symmetry lines are the crystallographic direction. Let's label them by A-axis and the B-axis. So if we look carefully at the step edges, we can find out that all the step edges is not actually random. Rather, it follows the crystallographic direction. The step edge looks grooved in the sense that the grooves follow the crystallographic direction. Now, the step edge direction is going to follow the way you're going to exfoliate it, and that's going to be a random direction, not going to follow the A or B axis, but it creates this grooves-like structure which tells us that it is easy to break covalent bonds along the B or A axis. And another way to put it is if let's say we are imagining exfoliation along some random direction, and this exfoliation direction is more closely aligned with B axis than A. So more bonds are broken along B than along A, along B than along A. And so that's why the wedge kind of looks like the red line is longer and the blue is shorter. And another thing to point out is that let's consider that this is a B vector, and if this is an A vector, then the C vector goes along the exfoliation direction. And that goes for each of these triangles. So now this kind of motivated me to look carefully as how it looks like in the form of a schematic on a sheet of graphene. And so I wanted to draw a schematic on this particular region by the yellow dotted box. And we find out that a sheet of graphene, when tiered along in this direction, looks like this, where when we tear it along, it creates this edge. And this edge is called as a zigzag edge. And so that brings us to understanding what are the other kinds of edges that exist on a sheet of graphene. And there are two other kinds of edges that exist on a sheet of graphene. One is the zigzag edge, and its name is zigzag because of the shape zigzag. And the other edge is called as the armchair edge because this is supposed to look like an armchair. Now, it's been theoretically predicted and analytically calculated that zigzag edges has localized electronic states on their edges. And this was theoretically calculated by the group of Japanese scientists during the 90s. And armchair edges does not have any localized electronic states. So what does that mean? So when they calculated the band diagram of these zigzag nanoribbons, they found out that these zigzag edges have something called as a flat band. Now, a flat band in a band diagram usually means that there is a higher density of localized electrons. And now these localized electrons, they are confined within some region on K space, and that can be converted to certain regions in the real space. And these are the regions where they're confined at the edges. So if there is no flat band, then there is no localization of electronic states. And that was kind of the corollary. And this flat band aspect is sort of is gaining a lot of interest in research these days. And we are going to use this flat band aspect to understand some of the features that we find on these edge defects. Now, this kind of brings us to the grain boundary because we are going to use the flat band aspect to understand the grain boundary. So to simply put, what is a grain boundary? It's a boundary between two grains. Now let's imagine that there is a grain over here and it has a crystallographic direction. Now let's twist this grain by some random angle, let's say 30 degrees. Now, when you bring these two grains together, you may notice that you cannot fill this boundary with hexagons. Now it has to be filled with other non-hexagonal polygons. And it was predicted by Oleg Yazov and Stephen Lowy in this paper that such a grain boundary gets filled up by pentagons and heptagons. And this prediction was actually later on experimentally proved in the same year by a transmission electron microscopy image, where they showed the existence of these pentagons and heptagons by Pinchman Huang. And she gave a talk last year in UCSD, and when I saw the talk, it kind of inspired me to look back into STM and find out these grain boundaries. It made me wonder, why can't we see this kind of structures in STM? And so I kind of started doing first a literature survey of STM imaging of these kind of grain boundaries. And because it turns out this is the most common grain boundary that you can find on graphene and graphite. And so this is an image of zigzag grain boundary that was taken in 2014 JAX. This is another in 2014 PRL, and that's in 2016 2D materials. And none of these images look like a zigzag grain boundary. Even worse, they don't match up. None of them look similar. And so what was the reason? And it turned out that this is because of what is called as, and because STM can detect charge distribution. What this means is whenever you take a regular sheet of hexagon and you fill it up with non-hexagonal polygons, some regions will get positively charged, some regions will get negatively charged. They'll kind of create electric dipoles, and they will attract electrons or repel electrons. And STM will be able to view all of that. But they seem to be voltage dependent. So I wanted to understand the charge distribution around these kind of grain boundaries. So I tried this new approach, which is the zigzag edge approach, where usually people in research, the way charge distribution is calculated is by something called as local density of states calculation, and that's kind of complicated. I kind of wanted a straightforward way to understand the local electronic charge distribution. So now let's consider this grain boundary, and what we're going to do is we are going to strip this grain boundary. And when we strip this grain boundary, we're going to look at the edges that is making this grain boundary, and we find out that this grain boundary is made up of a zigzag edge and an armchair edge, a zigzag edge and an armchair edge. Every pentagon and septagon pair has zigzag and an armchair edge on both sides. And so now we know that zigzag edges have localized electronic states. Armchair edges do not have any localized electronic states. So let's pinpoint those localized electronic states. When we pinpoint them, we see a zigzag pattern. And so this is a signature that I should be looking for when I'm doing STM imaging of these kind of grain boundaries. So I went back to my STM and I started hunting for these grain boundaries, and I found one. And it kind of looks like this, where we begin to see this zigzag pattern that is going all over the surface. And this is another two-dimensional, the same two-dimensional image that shows the zigzag pattern. Let me move this cursor. And now the zigzag pattern is not the only evidence that kind of tells us that this is the same grain boundary. Actually, it turns out there are other parameters that it has to fit. Like, for example,
I think it's because you clicked on the Zoom box.
Click on the presentation.
Yeah, so just click on the background. It should work.
thanks. So there are other parameters that it has to fit. Like, for example, the periodicities of this zigzag structure has to match, which it did. And the twist angle, the rotation angle at which these grains get rotated. Now, usually whenever you take pictures of atom, it kind of entices people in the crystallographic community to view it in reciprocal space. So whenever you take an FFT of these two hexagonal grains rotated at any angle, you can kind of see two hexagons that are rotated. And you can measure the amount of rotation angle, and that will turn out to be the same as this rotation angle. And which it did. When I did FFT of this entire two-dimensional image, I found two hexagons corresponding to the two rotated grains, and the angle of twist was 30 degrees. And so moving on, let me compare my image with all of these images that we have seen so far. This is a 2014 JAX image, this is 2014 PRL, 2016 2D materials, and here we are. We have come a long way since then, and you guys are looking at the best STM image of the most common grain boundary found on graphene and graphite. So, and this is the zigzag pattern that kind of matches with it. Now, if you look carefully, this STM image, it kind of tells you more information about this grain boundary, because STM has a lot better capabilities than other microscopes. And if you notice carefully, there are these hilly regions that we kind of see, and these hilly regions correspond to this outward deformations. Now, the outward deformations correspond to this particular atoms that are sitting over on these regions. And so let's measure what is the amount of that deformation and how much is the amount of deformation for each of these carbon atoms. So I'm going to draw a cross section along this line. And when I draw a cross section and I can measure the height is around 3.5 angstroms. And where is this 3.5 angstroms coming from? It seems like it was kind of theoretically calculated by Oleg Yazov and Stephen Louis in the same paper, that whenever you take a sheet of graphene that has a pair of point defect, like pentagon and heptagon, a pair of defect, it builds up a strain energy in the sheet of graphene. And this strain energy is released in the third dimension in the form of deformation. And that deformation was calculated by DFT calculations to be around 3 angstroms. And I measured it around to be 3.5 angstroms. Now, the extra 5 angstrom could have come for the fact that this is a 1D defect, whereas this is a point defect. So the 1D defect could have given that extra 0.5 angstrom. So it kind of tells us that all of these grain boundaries are sort of intrinsically buckled out of plane. Now, these kind of information you cannot get from a TEM image. Now, moving on, last year during my candidacy exam, I kind of showed this particular image of a zigzag grain boundary, and I said that this looks like a zigzag grain boundary, and I made this claim that it is the zigzag grain boundary. And I kind of remember one of my advisors, Bob, telling me that, am I supposed to believe that this looks like this grain boundary? And later on, I vowed that I'm going to take a better image, which we just saw. And this year, when I look back in time and I compare these two images, that makes me think that this may not have been the zigzag grain boundary, and I might have lied to my committee last year. And so I also made many other bold claims, like I'm going to take a tip and I'm going to bring it, put it on a pentagon and putting on a septagon and a pentagon. I'm going to measure the conductance at those individual tiny regions, at all of these tiny regions, a cheap animation showing that. Now, as easy as it looks, it is not, because the way you're doing conductance measurements, you're taking a tip and you're stopping over that region. When you're stopping over that region, you're sweeping the bias voltage. So it's stopping there at least for a second. And you have to make sure that it stays within this distance, within the 2.5 angstrom. So it has to be a low noise measurement. And so this idea is called as something called a spectroscopy of a grain boundary. So let's measure conductance of individual unit cells of these grain boundaries. Now I'm going to first start with the zigzag edges. Remember the zigzag edges that I was talking about, that has localized electronic states and a flat band. And this flat band exists around the energy level 0. And so what we are going to do is we are going to bring the tip close to the edges, and we are going to try to probe into these localized electronic states to measure, to see if there's even a flat band that exists on these grain boundaries. And so that's a curve of, this is di by dt, differential conductance. And on the x-axis, you have the sample bias. So the 0 over here corresponds to the 0 over here. And you can observe that there is a peak at 0 bias. And this peak, whenever you find a peak in a conductance, that actually corresponds to a higher density of states. Higher density of states would mean a flatter band, a band with lesser slope, because there is an inverse relationship between them. And so it does seem like there are zigzag edges, and we can probe into those localized electronic states, having this 0 bias flat band. Now, as we move down into the pentagon, we find out that the 0 bias states disappears. And instead of that, there are these other states that come into existence around 0.4 volts. And let's probe into the septagons. And when we probe into the septagon, it seems like septagons has a different structure where it has only single peak around the 0.4 volts. Now, I won't get into too much details as to why there are so many peaks here and there, but I kind of want to tell you the secret of how I image this grain boundary. And the secret lies in this conductance peaks. And if you notice carefully, whether you are on a pentagon or on a septagon, there is one peak that is common, which is the 0.4 volt peak. The 0.4 volt peak goes throughout the septagons and the pentagons. It exists all over this region, but not on the outside on the grains, only on the grain boundary. And this is called as a flat band of the grain boundary. And it turns out it was also theoretically predicted by Oleg Yadav and Stephen Louis in the same paper, a lot of predictions in the same paper. And this flat band of the grain boundary is distinct to this particular topological arrangement of pentagons and septagons. So now if you take another grain boundary, change the arrangement, these peaks are going to appear at someplace else, but there will be a flat band. And so the trick lies in the fact that whenever you are imaging, taking STM images of these kind of samples, you have to specify a sample voltage. And the sample voltage in this image was around 0.25 volts. So what this means is, let's say you put the sample bias to at here around 0.25 volts. All the states from 0 to 0.25 volts are going to participate in the tunneling process. And so there are no states over here, no peaks that are going to participate in the tunneling process. Now, when you increase the sample bias to a higher number, let's say 0.4 volts, the image becomes blurry. And this is very repeatable. So the image becomes blurry, and I'm going to tell you the same thing, that at 0.4 volts, all the states from 0 to 0.4 volts are going to participate in the tunneling process. Now, at 0.4 volts, there's a flat band. It begins to include this flat band into the tunneling process. So what a flat band means, there's a higher density of electrons. And these higher density of electrons are localized on the grain boundary. So it means that whenever you're imaging, including this flat band, it charges up the grain boundary. These localized regions are able to access the electrons, and these localized states become accessible, and they begin to get filled and they charge up the grain boundary. Now, when you reduce down the sample bias, it discharges the grain boundary because there are no states within here. So the trick lies with the fact that whenever you find these kind of grain boundaries, not just grain boundary, whenever you find any kind of topological defect, what you're supposed to do is you're supposed to find out where does the peaks lie. Are there any flat bands? If there are any flat bands, you're supposed to ignore the flat bands, avoid them if you want to image them better. Now, coming back to the same image, maybe it's my arrogance that I keep on coming back comparing my STM image with these guys, but let me point out what was the mistake that they did. Let's find out the sample bias that they used. -1 volt, 0.8 volts, 0.5 volts. The flat band lies at 0.4 volts, and you're supposed to avoid the flat band. And this was kind of the trick that kind of helped me in imaging these kind of grain boundaries. So flat bands are not the only flat bands are not only available are found not only on these kind of grain boundaries. It actually turns out they are also found on something called as moire patterns. Moire patterns are kind of interesting, and they are formed when you take two sheets of graphene and you rotate them or twist them on top of each other. You begin to see this pattern. Now, in this pattern, you will notice that there are these circular regions over here that are arranged in some regular arrangement, and these circular regions are called as AA domains or AA stacking. In these regions, the hexagons of the top layer are sitting right on the hexagons of the bottom layer, and so there is maximum repulsion between them, and so they have a very unstable stacking mechanism, and they're weakly bonded. But the surrounding regions are called as something called as AB domains, where AB domains is the most stable kind of stacking mechanism, where the hexagons of one of the layers get shifted by a half a lattice constant. And so there is more interaction, more coupling between the top layer and the bottom layer. There is a stronger interlayer coupling, and here there is a weaker interlayer coupling. Now, this is a very broad definition of defining moire patterns. There are other domains that we'll get into later on. So let me first show you this simulation that was developed by one of the students in Prav's lab, Shreyam. And this moire pattern, it shows a moire pattern as a function of the twist angle and how it looks like. That's the twist angle at the bottom, 2 degrees, 3 degrees, 4 degrees. And you can see how these circular regions are coming close and closer and closer. They're coming so close that now we cannot see them. But the period, the way this periodicity changes is from 0 to 30 is the same as 30 to 60 degrees. So the period is sort of 60 degrees. And we are going to see that as it's going from 30 to 60, the periodicity is going to increase. All of these circular regions are going to diverge. Going out, going out. There you go. And that brings us back to 0 degrees. So this was an image that was captured at 7 degrees. So it turns out that moire patterns are also found commonly on graphite surfaces. And this is a 3-dimensional image of a moire pattern that I found on a graphite surface. And this is at 4 degrees. And each of these individual dots that you see are called as, are individual carbon atoms. So the hilly regions are called as the AA domains. They have weak interlayer coupling, so they are pulled out of plane. Whereas the valley regions, which are the dark regions, are called as AB domains, where there is strong interlayer coupling. That's a 2-dimensional image of the same 3D picture. And you can see that these are the hilly regions and the dark regions are the AB domains. So let's draw a topographic line along this red line that I've drawn over here, and that red line goes over AB domains and the AA domains. This is the schematic showing the same, that the AA domains are the hilly regions, and the AB domains are these strongly bonded regions. So let's try to deform this moire pattern. We have now learned how to deform them. So this is a topographic line, topography along this red line drawn over here, where all the hills are the AB domains, all the valleys are the AB, all AA domains, all the valleys are the AB domains. Now we know how to deform them. All we have to do is bring the tip close to the sample. And I'm going to do that by increasing tunneling current by an order of magnitude. This is taken at 10 nanoamps. So let's increase the current to 100 nanoamps. And we observe that these regions have got deformed. They have been pulled outwards out of the plane. And so now we can measure the amount of deformation on AA domains compared to the amount of deformation in the AB domains as a function of this tunneling current. And we will find out that it turns out that the AA domains get deformed by a much larger amount in contrast to the AB domains. And it kind of tells us that these AB domains are easy to pull out of plane. And these AB domains are not that easy to pull out of plane. And this is just a schematic trying to show that the AA domains are easy to pull out of plane, and the AB domains are sort of the anchoring regions, not letting the moire to get pulled upwards. And that kind of tells us the strength of the van der Waals bonding, this test. And it tells us that the AA regions are weakly van der Waals bonded, and the AB regions are strongly van der Waals bonded. And that kind of makes sense because the AA stacking has weaker interlayer coupling. It has larger repulsion, whereas AB stacking is more strongly bonded. And so that's why AB regions got deformed by a lesser amount in comparison to the AA domains. Now, whenever you're trying to deform a moire, we understand that there are mechanical regions that get mechanically deformed. But what about the electronic deformation? What happens electronically? And so if we bring down the tip on these hilly regions, it turns out that these hilly regions also have something called as a flat band at charge neutrality. Now, as we deform these moire domains, let's measure the conductance as a function of these deformations. Now, when we do that, we observe that the peaks are going narrower and narrower. The peaks are going sharper and sharper, and we can measure the amount by which it's going narrower. We can calculate the full width half maximum, which is around 100 over here at the bottom of the curve, to 75 millivolts, which is the lesser full width half maximum. And it kind of tells us that these bands are also getting deformed, and not just the mechanical domains are getting deformed, but the electronic bands are also changing the structure. And there's an image that shows that this electronic band is formed by two peaks, and these two peaks have come closer to each other as a function of these deformation. So now that kind of brings us to an end to this idea that when we are using the interatomic tip forces from the tip, we can not only mechanically deform these moire regions, but we topographically deform these moire domains, but we can also change the electronic bands as a function of deformation. This aspect is called as strain engineering, and this is the topic of my dissertation. What we are offering here is a novel approach to engineer strain in a way that there are other conventional ways of strain engineering is by twisting two materials or by applying pressure through polymer stacks. But what we are offering here is a controlled atomic deformation using a tip's interatomic forces. And so where do we go from here? And that kind of brings us to the future work. In the future work, we will talk about domain walls. Domain walls are another kind of domains that exist on the moire patterns, and we'll look at these moire patterns from the perspective of the domain walls. We'll also look at magnetism and grain boundaries. And the third one is OH negative ion manipulation. So you saw this image of a twist angle of moire pattern at 4.2 degrees. Now, we know that this is another image at 0.5 degrees. Now, if you notice the scale, this is 5 nanometer and this is 30 nanometer. And all the bright regions are the AA domains, where the hexagons are on top of hexagons. All the dark regions are the AB domains. So what is this extra structure that came into existence as we changed the twist angle? We did not see this pattern on a different twist angle as well. So it turns out all the dark, when we see this alternating dark and white triangles, all the dark regions are topographically downwards, or they're elevated downwards, and the white triangles are elevated up the plane. So these white triangle regions are something called as rhombohedral stacking. And these rhombohedral stacking is another kind of domain that comes into existence only in the case of tri-layer or multi-layer Moire patterns. And the boundary between them, which is represented by these dotted lines, is called as a domain wall. So now let's look at these Moire patterns, but let's only look at what happens to the domain walls as we change the twist angles. So where is the rhombohedral region in this case? So let's draw the domain wall on this, and that kind of tells us that this rhombohedral region is kind of shrink to such a small area that we cannot actually see. They do exist, but we cannot actually see them. So let's compare it from the perspective of domain walls. The domain walls at 0.5 degree looks like straight triangle, isosceles triangles. At 1.2 degrees, these domain walls of the rhombohedral region squeezes, and it squeezes even more. And so the amount of area that's being occupied is going lesser and lesser relative to the Bernal region. Now let's deform all of these Moire patterns. And another thing to point out that the length scales that you have drawn over here, 3.4 nanometer, 30 nanometer, 30 nanometer, these are all different. So you kind of have to imagine that these are of a much bigger length scale than this. And just to help with your imagination, I've put this picture over here where these are not now of equal scales. And all these bright regions, the AA domains on this, as we go down the twist angle from 4.2 degrees to 0.5 degrees, you can imagine now all these bright circular regions, the AA domains, are being stretched. Now, when you're stretching them, it's stretching these domain walls as well. So the domain walls are changing the shape as a function of these twist angles. So now let's deform these Moire pattern and let's see what happens. At 4.2 degrees, we do not see much change in the shape. But something interesting happens at 0.5 degrees. We begin to see this kind of shape of a Mercedes symbol, and this white dotted line kind of shrinks in diameter, shrinks in size, the rhombohedral region, and the black dot region, which is a stable Bernal domain, grows in size. From a triangle region, it grows in size, and so this is a stable region that is kind of growing in size, and this is a lesser stable region that is shrinking in size. And one way to understand this qualitatively is that Moire patterns are always under strain. In other words, whenever a Moire pattern is sort of a competition in terms of strain energy between two domains, and these domains occupy certain areas. And so the relative ratio of these areas is the competition. Now, when you apply deformation on Moire patterns, it adds strain energy to these surfaces. Now, the competition, the addition of the strain energy is going to act in the favor of the stable regions. So the stable region will grow in size and the unstable region will shrink in size just to accommodate for this extra strain energy that I'm applying by deformation. Now, I've looked at many other angles starting from 0.5, 0.4, 0.3, and 2 degrees, 1.2 degrees. And when I look at all of these angles, I kind of came to a realization that something interesting is happening at the 1.1 degree, as if this is some kind of a turning point. These domain walls change their shape into this kind of Mercedes symbol, but beyond 1.1 degree, that does not happen. It only happens under 1.1 degrees. So something interesting is going on in around this magic angle region, and this is something that could be explored further. Also, there is very limited research on domain walls. It's something that has been recently talked about for the past year. And these images that you're looking of domain walls, it's a very new perspective of understanding Moire patterns. Moving on to grain boundaries. Last year, before my candidacy, I kind of made this accidental discovery that where I wanted to test if these grain boundaries could be magnetic or not, but I didn't have the right equipment. So what I did was I took an STM tip and I wrapped a coil around it. It's a current carrying coil. And so when I turn on the current in the coil, it will create an electromagnet. So when the current is turned off, this is how the grain boundary looks like. Now, when I turn on the current, it seems like there's regions around the grain boundary that is responding to this magnetism, the electromagnetic forces. And so it could be possible that these grain boundaries could have some spin filtering mechanism. Now, usually the deal with magnetism is that you cannot just show qualitative pictures. You have to measure the amount of magnetic moments, you have to show the hysteresis, you have to sweep magnetic fields. And so these are the kind of things that can be done in future work. And coming to now to the OH ion manipulation, this is a schematic showing how an OH magnet sits on the surface of graphene. And I have imaged single hydroxyl ions on the graphite surface. So this is an image of a single hydroxyl ion sitting on a graphite surface. That's the background sheet of graphene. And that black dot is an OH negative ion. This is a three-dimensional image of an OH negative ion protruding out of the surface. And I can measure the amount, the height of this OH negative ion. And it turned out pretty close to the bond lengths of carbon and oxygen and hydrogen. So now what if we bring the tip closer on this OH negative ions and we try to move it on the surface? So what I did was I found a bunch of OH negative ions on the surface and I wanted to move. I didn't want to move. I just wanted to play around with these OH negative ions. So I tried imaging them at a smaller gap. And I found out that if I track this particular atom, it moved to the bottom of the screen and these two remain intact. And it kind of tells me that I either picked it up or dropped it off, or I dragged it. But I wanted to just point out that one can also play around with OH negative ions movement on the graphite surface. And this kind of brings me to the end of the talk. To summarize, in the first half of my PhD, in the first two years, I used to grow graphene, synthesize graphene by chemical vapor deposition. This is an image of a CVD graphene flower that I took on a copper surface. It's an optical image. And it's for the last 2 years, I've been working on the STM, and this will kind of give me my future publications on strain engineering and on the zigzag grain boundaries. I want to equally acknowledge my advisors, Professor Bob Dines and Professor Prab Bandru, for giving me all the freedom in doing all of this research. And I also want to shoot out a special thanks to Mike Resin, who was very important in the technical aspect of the technical circuitry element aspect of the STM electronics. I want to thank my postdoc Uday and all the current and graduated members of Prab Bandru's group. And I also want to acknowledge some of the modern equipments that I have used during my research. Like, for example, this is a Windows 98 computer that I use. It's an Intel Pentium 2, I think, and it works only with a floppy drive. So all of these images have been transferred with floppy drives. One time I was ejecting the floppy and the whole drive got ejected, but now it's working because I put a tape around it. And usually whenever you're working with microscopy or the tip-based microscopy, you buy tips commercially from industries, and they usually cost over $200. I used to make tips of my own bike with a pair of scissors and a wire. And it looks simple, but it's a tough craft master. It took me months to master this craft. And whenever this is the last slide, and whenever you Google a sheet of graphene on a surface, you'll find this particular image of these carbon hexagons. Maybe it's my arrogance that I have begun to compare my two-dimensional images with these kind of schematics, but there's a little too much noises over here and there, and there's a lot of work to be done, and the horizon is still far. We have a long way to go. Thank you.
Thank you, Nirjhar. Unique, outstanding, excellent. Yeah, I think we'll follow protocol. Take questions from the audience.
It was a really good talk. For the Moire patterns, when you're doing the twist angle, that's like 2 layers, right? So then how do you get like the tri-layer stacking, like the ABA?
So these Moire patterns are created on a graphite surface. Yeah, so it's multiple layers. And so I don't make them. They actually are naturally found on the graphite surface and they're formed during the exfoliation. So if you buy a bulk graphite and to try to image them, then you're not going to probably find them. If you exfoliate them for a while, then they are formed on the graphite surface naturally. And I think it's the only material that I've known that naturally favors the formation of moires. And so it's a good platform to study moire patterns with.
Yeah, so as a follow-up question to that, like, is there an experimental way of like knowing, like you saw those domains, right? Like, they could, how can you be sure that they are like coming from just like 2 layers of graphene, but it can be effectively coming from multiple layers?
If it's coming from multiple layers, usually it's becomes moire patterns on top of moire patterns. Now that does not look like regular arrangement of circular regions, then you will see multiple interferences of 2 moires. So it's kind of easy. I have images that show that these are multiple twists and not a single twist.
Other questions from people on Zoom?
Oh, yes.
They're looking very quiet. Well, since this is an examination, we have to ask everyone in the audience except the committee to please go out and cool your heels somewhere. And we'll keep Nirjhar in here for any questions that the committee wants to ask of him. Then we will kick Nirjhar out and he can cool his heels.